Okay. Let me remind you quickly what we have done last week. I introduced this notion of partially ordered set. It's a useful notion. It's a set with a law or a certain comparison between some elements, but not all of them are comparable. And I also introduced this notion of left complete tree. And whenever you know these two ingredients, you can discuss or introduce what is a priority tree. It's a way to organize a partially ordered structure. So before we had a tree with a fully ordered structure, but if it is only partially ordered, you can use this notion of priority tree. And I said that you can try to write an algorithm for extracting some information from this tree, or for removing one vertex, or for adding one more information on this tree. Then we had this short section about counting binary trees or labeled trees with n vertices. This is more about combinatorics, how to get some numbers about the number of trees. Still, it's interesting because these numbers, first, they are growing very fast with the number of vertices, but it also gives us some information about if we have an algorithm and we have to treat n power n trees, it's probably very slow. If you can decrease the number of possibilities, then it becomes interesting. So knowing the number of trees has application also for algorithm. Spanning tree, it's a tree inside a graph. So we have two kinds, either an undirected tree or an arborescence when you have a row going always away from the root. So, and this notion of spanning tree is important. So let me give a few definitions. A tree inside a graph. So you have a complicated graph, whatever. And a spanning tree is a tree on it, let's say like this. This is a, no, yet it's not a spanning tree because we don't touch all vertices, but now it is. This is a spanning tree inside the graph. So whenever you have an edge, you can discuss what is a tree edge or a tree vertex or a non-tree edge or a non-tree vertex. I introduced this last week. And also what is a frontier edge. I also introduced it last week. And I mentioned one algorithm for growing a tree. It was made of 3 points. And I said the second point, we are still going to discuss it because you have lots of freedom in the second point. And we are going to see two possibilities today. And when you grow your tree, whenever you put one new when you put a new edge, you assign a discovery number. And at the end, you obtain with this ordered tree. And finally, at the end, so when you grow a tree, you obtain, let's say, this from a certain graph. You can add the edges which are not in the tree, but in the initial graph. And you have two types, either the yellow one like here, or this one, and they have different names. The yellow one is a skip edge. What it means that this edge has one endpoint, which is an ancestor of the other one. So this one is the ancestor of this one. And the second kind of edge is cross edge. It's called cross edge because neither this point nor this point is an ancestor of the other one. Last week, it was a little bit imprecise what I mentioned for cross edge. So be careful. You start with a graph, you obtain a tree from this graph, and then I'm just adding the missing edges compared to the graph, and they are divided into two types, either skip edges or cross edges. If you have any question, you can interrupt me at any time, of course. All right, so the first part, I'm going to mention two ways to use growing a tree algorithm, but with two solutions for the point 2 in this algorithm. So the first section, 4.2, is about depth first or breadth first tree. or search. So I will explain what are these two words. So the first one, it is depth first search, which I'm going to abbreviate DFS. So what is it? First, I write a sentence. The idea is to explore. So remember, what I want to do is to create a tree inside a graph. So it's explore as far as possible. As far as possible before backtracking. This explains the word, but now I need to be more precise. So in point 2 of the algorithm about growing a tree, it was take one new edge in, the sentence was take E inside front GTI at the step I. And I said, you have lots of freedom. If this set is big, so maybe I should draw a picture. Suppose we have a very simple tree like this for now. This is TI. Suppose the blue one is TI. You have many elements in front TI. You have this one, this one, this one, this one, this one, because all these edges have one endpoint in the tree, in the blue part, and one endpoint which is not. So we have all these elements in this set. And so what is this algorithms is when choosing this new edge EI plus 1 in front of GTI, choose one. We have choose one with I will explain. So we choose one with 3 vertex, which is the same as 3 endpoint with largest I. So this is a key for this type of algorithm. So let me explain. Right, suppose we are at this step. I need to choose a new one. And if I follow this rule, it means I need to choose a red vertex with one endpoint with the largest I. So here I have the largest I is 2. So if I follow this rule now, I should choose either this one or this one. I should not choose these 2 or this one. Right? So this is this, and we will see why it's, this is an interesting solution. Whenever we have to choose one in this tree, we choose a new edge with one endpoint with the largest I. Still, it doesn't mean it's unique, but it eliminates some other solutions. So this is called a depth-first search. There is one picture in the notes. But yeah, let me draw again a graph. If I follow, let's say I start here. This is the first one. Then if I always follow this rule, it means I start from here. Now, if I continue with this algorithm, I need to start from here. Then I have to start from here. Then let's say here. Still, it's not unique. I had a second solution at one point here, now here, and let's say this one. This is it's not a spanning tree yet, but at least it has, I follow this rule. Yeah, I'm not saying that this is the end. Choose now, indeed, what is the next step? The next step, I can still continue, you're right. I can continue here. And I already covered everybody. But for a second, suppose that I had a second part here. It's not a spanning tree. The yellow one is not a spanning tree. So now I'm here. The last one was here. I cannot continue because this is not in front of GTN. I don't know, this one is not. Still, I have two here. And I need to apply the rule. So which one I'm going to choose? Can you tell me? The up one or the one bit? Down one. Yes, because this point, I didn't write the number, but this one has a number which is bigger than this one because this one was 0. So it would be this one. And now I have a spanning tree. And check this is a tree. So this is one algorithm. Always choose one endpoint with the largest I. Still, it might not be unique. And the result of this algorithm, the result is called DFS tree, depth first search tree. What you observe on this example, of course, it's not a perfect rule, but these trees are not balanced. You remember balance means more or less you have the same length for all branches or all parts of the graph. Clearly, this is not a balanced one. If you draw it as a tree, you will see it's not balanced. But of course, this sentence cannot be very precise because it depends on the initial graph. But as a rule, you can easily guess with this procedure, you have a very long one, and then the other one are shorter and shorter. Lemma, and I'm happy if somebody try to prove it, it's very easy. For an undirected graph, this algorithm also applies to arborescence if you have orientation, but as we have seen, it might not finish. You might not get a spanning tree. So for undirected graph, a DFS tree has no cross edge. So you have to remember what is a cross edge. It was on this blackboard before. And you need to check that if you draw a graph following this or a tree following this algorithm, you have never any cross edge. It's not difficult, but you have to think what means a cross edge and why this will not happen. So probably you can do it by contraposition. Suppose you have a cross edge, then at some point you didn't use this algorithm. But it's a good exercise. So somebody was looking for an exercise. It's a good exercise because you need to remember the definition of a cross edge, and you need to think about this algorithm. But once you understand, it's not difficult. And let me write another sentence, which is not very precise, but somebody can try to make it more precise. There exists a natural link between pre-order traversal and so this was NLR. When I introduced the traversal, I introduced 4 types, and one was pre-order traversal, and it was abbreviated NLR, and DFS3. So if you think about it, you construct your tree, and I didn't write the numbers, but you have the discovery numbers. Then there is a natural link between the tree you're going to obtain and where you can find these discovery numbers and this pre-order traversal. Remember, a traversal is one way to systematically visit a graph or a tree. And there is a natural link between these 2 things. Again, it's good to remember. However, there is a small thing hidden here. When I introduced pre-order traversal, I did it for binary trees. Here, you are not always going to obtain a binary tree. You may have 3 branches. If I had something like this, then the tree would have one more here. And at this vertex, you would have 3 edges going. So it's not only a binary, it can be bigger than a binary tree. Still, it's an ordered tree. And you can easily extend this notion of pre-ordered traversal, not only for binary tree, which you have left and right, but if you have 3 children, then you have the first one, the second one, and the third one. So this notion of pre-order traversal can be extended to any p-ary tree if you have p children. But if you think about it, there is this natural link between these 2 notions of pre-order traversal and this tree we have just constructed. I encourage you, these kind of exercises are not difficult, but you need to think about the definitions, because that's the point. All right, so in this algorithm, choose always the one with the largest I. Of course, the second one is with a minimal one. So I'm going to introduce the second algorithm. The second one in this section is Breast DTS. DTH. First search, which is going to be abbreviated BFS. And now the sentence is explore the neighborhood. So before it was go as far as possible before backtracking. Now it's explore locally. So what it means when choosing EI plus 1 inside front of GTI, so just step 2 of the algorithm, choose when choosing, take one with minimum end point xi, or minimum I for endpoint xi. So when you take it, I should have a permanent graph on this blackboard, which does not go out. So let's see, this is E1, E2, E3. Suppose I have already done this part. Now we have several edges in the frontier edge. I need to take one with a minimum endpoint. So I have only two solutions here, is this one or this one. Or let's say this is going to be E4. And then what is E5? The other one, this is E5. And if I continue, which one is going to be E6? Now, I cannot go further from E1, from this point. So I need to go here. And I have only one solution. This is going to be E6. Right? And then E7, it's going to be this one, indeed, E7. So what you see, you are indeed going by neighborhood. You first go around this one, then around this one. Now I cannot go any further. So I move to this one. Here, I cannot do anything. So I move to the next neighborhood, which is this one. And you can already see something if you draw this tree. In general, it's going to be more balanced. Again, it's not a fixed rule, but let me just write in general. The spanning tree is more balanced. Be careful. I'm sure you can construct an example which is completely unbalanced. But as a rule, if you think about it, it's more likely that the graph is balanced. And the resulting tree is called, you can expect it's a BFS tree. And in both cases, whenever you have, here, remember, we had a choice, not this one. The algorithm doesn't tell you which one to choose. So either you have another rule, depending on what you do, which tells you take one or the other one, or you do it randomly. This is called a default priority. So when choose default priority. In the algorithm, there is no reason to choose one or the other one, but maybe for some other reasons, external reason, you have a reason to do a certain choice or to do it randomly. Yes? Yes. But again, it's not, if I start with a tree which is like this, I start already with a tree. And now I ask you to do this algorithm. Okay, you're going to do it, but what you're going to get is very unbalanced because you're going to get this one. So you cannot say for sure it's going to be balanced. But if you take an arbitrary graph and you do both algorithms, most probably the first one will be rather unbalanced, the second one will be balanced. But
when you say in general, there are instances when DFS can be more balanced than BFS.
I'm sure you can construct an example where at least you have an equality that if you do both algorithms, they have the same structure because you're going to get this one. Now, the notion of balance is not very precise. I haven't given a precise definition, but it's more feeling. And in applications, it is interesting because if your graph is balanced or not, some algorithm go faster or not. And now again, there is this natural link that somebody can explore. What is a natural link between a certain type of traversal, which one it is a level order traversal, which is the first one I had introduced, the up, down, left, right, and this BFS tree. You can see if you apply this algorithm for the traversal on a BFS tree, you are going to get the discovery number in a very specific order. Lemma, now this is more precise. Let X and Y belong to the BFS tree with a level of X smaller than the level of Y. Where do I have a tree? Okay. Yes. This is a tree. Move this. I just keep the structure of the tree. This is a tree. It's ugly, but it's still a tree. The level 1 are these 3 vertices. Level 2 are these 2, and level 3 is this one. So it means if I take a X, which is at level 1, and a Y, which is at level 2, then the DF number of X is smaller than the DF number of Y. It's not visible. This would be X1, this is X2, X3, because I associate this number to the edge having this DF number. And we would have X4, X7, oh, okay, it's no more correct because I remove some edges, but and so on. So you have this relation between the level in the tree and the time you discovered the vertex, which is not true in the first kind of trees. And the second statement, this was the first part of the statement one. The second part is any BFS tree it provides the shortest path tree. For any unoriented. So if you start with an unoriented graph, you fix for fixed root or fixed root. So you take an unoriented tree, you fix a root, and then you draw this spanning tree according to the BFS rule. You are going to get a tree. And if you just look at this tree, it gives you the information about the shortest path. It's what is called the shortest path tree. It gives you the shortest path between the root and any point in the tree. So this algorithm allows you to construct the shortest path from the root to any point. And the height is the distance, or the level gives you the distance between the root and any vertex. Okay, so this is a nice way to construct systematically this shortest path tree. Just use this algorithm, DFS. Do you have any question or remark? Okay, you can always ask me. Now, the next section is a little bit long, but at the end we have nice application. Of DFS, so the first approach. Let me just tell you what is the idea at the end. Suppose you have a graph. I do it explicitly like this. Suppose we have a graph like this. There are a few places which are quite special, a few edges which are quite special. This one and this one are quite special, and they're going to have a name, because if we cut them, we get a disconnect graph. So can we find an algorithm, or if you have a complicated graph, how can you detect the weak, these are the weak points or the weak edges, because as soon as you cut them, it's disconnected. Is there an algorithm for finding them? And this is what we do in this section, and it's going to be an application of DFS. But I need to introduce a few things before. So in DFS, remember, you should keep in mind EI plus 1 as minimum, no, maximum. Has largest endpoint in xj. Just remember, when you choose a new one, you look at the set font of GTI, and you look at one with the largest endpoint, the largest J. Just keep this in mind. Okay, so one definition in a DFS. So in a depth first search, discovered vertex is finished. It's finished. I need to give you the definition. When all its neighbors have been discovered, and those is, it's not an easy definition, but when you look at it on an example, it's easy to understand. And those with higher discovery numbers are also finished. Probably there should be a better definition, because it's a kind of iterative definition, because I define what is finished by looking at what those who are already finished. I'm not happy with this definition, but what it means. Okay. Suppose we start here on this example, x0. I do E1, we get x1. Then I need to take a new edge starting from x1. Let me take the yellow one. This is E2, x2. Then I need to start from x2. I take E3, and I get x3. And the last one, E4, x4. Of course, I can continue then from x0. But what means finished? Look, x4 is finished because all its neighbors have been discovered. Its neighbors are x3 and x2. Now, in fact, X3 is also finished because the one with a higher discovery index is finished, and so on. So it's when you cannot move further in this. On the other hand, X0 now is not finished. So you can go here, and this would be E5, and you can continue. So on an example, it's rather easy to understand this, finished or not finished. It means you cannot go further, and the one with higher discovery number are themselves finished. Okay, so I need this definition of finished. Maybe I can write an exercise. If somebody has no idea. Again, it's establish a link between NLR traversal wait, no, it's not the correct one. It is LNR traversal and also the other one, LRN traversal, and the notion of the DF numbers. I will explain. It's too complete. This sentence is too complicated. So, what is it? Find a link between either, so I should write probably either this traversal or, oh, it's better. Find a link between either this traversal or this one and the notion of DF numbers and finished vertices in a DFS. So again, it's not difficult. Draw an example, check. When you draw an example in a DFS, these DF numbers and finished vertices are very precise. And then you read your graph, your resulting tree, either with a NLR traversal or this one, and you will see that either you get exactly the list of DF numbers in an increasing order, or you get the list of DF of finished vertices. So draw an example, and then you see what happens. But if you do this, you're obliged to remember these few definitions, which is certainly good. All right, so still in this example, look, before backtracking, I've done this, which is a pass. Pass is you go through vertices on edges, but without going 2 times to the same vertex or 2 times to the same edge. This is the notion of pass. So I'm going to give a name to this before the first backtracking. So before I go back to another point, I will call this a DFS pass. Definition, a DFS pass is a pass produced by DFS, depth first search, before before the first backtracking. Or before the backtrack. And it's clear. In this search, you go further and further and further, and suddenly you have to stop. So you just call this, before you have to stop, you call it the DFS pass. This example is slightly too simple, but what do you observe about this guy? This is the last point before, the last vertex before you backtrack. Observe that its neighbors are in a cycle. It's a very small cycle, but nevertheless, its neighbors are in a cycle. Is it always the case? Yes, it is. Why?
What if you remove the white edge?
If I remove something, I'm cheating. Okay, you're right. No, okay, good. In fact, I'm wrong. You have two alternatives, and it is in the next statement. You're right. If I remove this one, it's not a cycle, it's a leaf. The point is a leaf. So we have two alternatives. Thank you. In fact, you find a mistake. You have two alternatives. Either when you stop, all neighbors are in a cycle, or I remove it, it is a leaf. I cannot go further. There is only one edge, and you already use it. So let me state this as a lemma. And again, it's a very nice, the proof is given in the notes. If you look at it, it's a nice construction. So let me state the result. Lemma. I take a undirected graph. In this topic, it's mostly undirected because otherwise it stopped too quickly most of the time. And let X, I need to give a name. So this one, the last one, I will call it XF, or finished. Let XF be the last vertex of a DFS pass. Then either XF is a leaf, which is one alternative, or this is all neighbors of XF are in a cycle. How you prove it? You do it by contradiction. I let you think about it, but first, they all have to be in the pass, because if they are not in the pass, it means you can continue. You don't have to backtrack. So first, you observe that they are all in this pass. And then you look at the DF numbers. So I come back to this picture. In the pass, and on the set of neighbors, they have a DF number. You take the first one, the one with a minimal index, and then you observe that maybe you are not directly going back to X4, but you will do something and go back to X4. So you have a cycle. Again, if somebody is interested, you can just look at the proof. Oh, but this is interesting because what it says. It said that if I just apply this algorithm automatically I find some cycles, because as soon as I need to backtrack, all neighbors of this point are in a cycle. So I have a way to find cycles. So let's keep this in mind. Remember, my aim is to find the weak points. In this example, it's already visible, something. I create a cycle, and which can, by definition, a cycle cannot cross a bridge, because the definition of a bridge is whenever I cut it, I have a disconnected graph. Okay, so let's keep this in mind. This DFS paths allow us to find cycles. I told you it's a rather long section because we need a few ingredients. This is one of them. Now, I need to be more precise about this picture. Definition. Let G be connected. And let B be the set of all bridges. So here we have these two yellow vertices, these two yellow edges, sorry. Bridge, it's an edge. A bridge component is a component of G minus B. We cannot, so this is definition of what is a bridge component. A bridge component. What it is? G minus B, we know what it is. We remove all bridges. So it means I delete this one, I delete this one. So I get three components. This one, this is a bridge component. A second one, which is this one, and we have a third one, which is here. So if we eliminate the bridge on this graph, we have three bridge components. Right? This is a rather simple notion. Still, it's interesting. Of course, I'm cheating with this definition in the sense that I'm already, it's a definition, I'm already saying that I know these bridges. The aim of the algorithm is, at the end, is to find these bridges. But for the definition, I'm allowed to take it as, suppose we have all B, and I give a definition of what is a bridge component. But the final aim is to find these elements in B. Again, if you have any question, interrupt me. Otherwise, I feel it's too simple. No, not only you, somebody else. Yes.
We didn't define bridge yet.
Bridge, of course we did it. Look in your notes. A bridge was defined exactly as one edge, such that when you remove it, you get at least one more component in the graph. Sometimes more, no, it's, yeah, maybe sometimes more than one more, but at least one more. So here it's clear, if I remove this edge, the graph is made of two components. If I remove this one, the graph is again made of two components. So yes, we define what is a bridge. It's also called a cut edge. Bridge is, yeah?
Is it possible to have more than one more component?
Okay, I'm not sure. For if you remove some vertices, this is clear. For edges, maybe not. Maybe for edges, it's always one more component. But I cannot imagine an example where we would have more. Yeah, so I suspect that it's only one. On the other hand, for cut vertices, you can have more than, because cut vertices means I remove everything here. So we have four components, these four dots. but for cut edge, I guess it's only one more component. You can try to prove it, and it's probably not difficult. I didn't check. Okay, now the last part in this construction is, I know that by removing the bridges, I can create different components. I would like now to shrink these components to one point. And this is the next notion. Keep in mind shrinking something. So let H, it's a set of vertices on a set of edges, be a subgraph of G, which is V and E. Now the contraction of H is a replacement of VH by a single vertex, which I'm going to call K, and replacing any edge. I will make a picture. So I replace all vertices by one, but for edges, I need to be careful on replacing any edge between a vertex in VH and a vertex in V minus VH by a vertex between A and the endpoint. Okay, it looks complicated, but if we do it on a picture, it's not so complicated. So let me draw certain graphs. This is G, and I decide that this part the yellow part is H. It's arbitrary, an arbitrary subgraph. So if I do this procedure, the contraction of H, it means first I copy the white part. No, I fix K. So it means these three vertices are just going one of them. Okay. And then I need to keep some edges. The edges which were between one element of H and one element not in H. So this, and this have one endpoint in H, one not in H. So it means from K, I need to do two to this point. So let me call this A. This is A. Then we have B and C. B and C. And I need to do two edges between K and B. This is a contraction of H. I put all vertices in one point. Some edges disappear, the one inside. So maybe you can add elements or edges edges in EH, they disappear. They do not appear anymore. But you have to keep track of the one connecting one vertex in H and one outside. And these are the 4 you can see. So this is a contraction. And you can, whenever you give me a subgraph, I can do it.
How about this subgraph is not connected?
I guess it works. I didn't try, but no, the definition that the initial graph.
Doing it respectively for each component.
I didn't test it. Okay, so in this case, I would have to, this is the only other possibility. Yes, it works as well. Now I shrink also. Okay, right. Probably in this definition, it's I need connect. The H has to be connected. So let H be a. I don't think I took it in the notes, so I have to be careful. Add, please, the word connected. I'm not sure it works because without this word connected, I should put 1K for both parts, and then I have a problem. So you're right. I should keep the word connected. And when I'm going to use it, it will be connected. So yes, please add connected in this definition.
Sorry, Professor.
Yes.
Shouldn't it be by an edge between K and the endpoint in V minus VH?
What edge do you want to add between K and?
The definition in the last 2 lines, not vertex, but edge should be there, right?
One says vertex, where it shouldn't say edge. No, on the middle one, second line.
Second line.
Yeah, on the middle one.
And so in the middle, the second line.
But oh, you're right. It's not a vertex. Thank you. This is an edge. Is it correct? Yes, I draw an edge between K and the endpoint. Yeah, thank you. Sorry. And yeah, connected is probably necessary in the definition. You can check what happens if it is not connected. Probably we get something meaningless. Okay. And now a statement before the algorithm, and the algorithm is your job, you see. Lemma. Let G be connected. And undirected. By contracting each bridge component, and by definition, a bridge component is connected. So I've satisfied this additional condition. By contracting each bridge component, one obtains a tree. Again, it's not difficult. Let's just check on this example. If I contract, as we have seen, we have 3 bridge components. If I contract, I have just 1 point here. So I put 1 point here. I keep this edge. And I have a second point here and a third point here. So the result of this construction for this graph is indeed a tree. It's a very simple graph. But look what we see in this picture, it's already visible here, is that, in fact, what we get are these two weakest points, or these two weakest edges. And what is the algorithm? It's written in more precisely in the notes. I'm not going to write it, but if somebody wants to study it, it's most welcome. Now, remember, we have two ingredients. We have this notion of bridges and contraction of the bridge component. But we have also seen that with a DFS tree or DFS path, we obtain cycles. And the final observation is a cycle can only be in one bridge component, because otherwise it's not a bridge. If it links, a bridge means precisely there is only one way to go from one place to another one. In a cycle, you have always two ways. So observation, I should mention it. A cycle can only be in one bridge component. It cannot be between two bridges component by definition. There would be a contradiction. Okay, now what is the idea or what you can do? Is get the tree of the previous statement with the DFS or DF search or DFS pass, I should say, with DFS pass contractions over cycles and the lemma about the endpoint of the endpoint of a DFS pass. So there is still something to do, but you have all the ingredients. So take a graph, do a first DF pass, then you have a cycle. Now we know what we can do with a cycle. We can, is it still here? We can contract over the cycle. So all points in the cycle, and it's connected. So it satisfies this additional thing. We contract it. And if we think about it, if we do this process iteratively, we are going to get exactly this tree. So without, the point is we don't know the bridges. Before I said in this definition of bridge components, I'm using the notion of bridges. We don't know it. So I'm not allowed to use them for the construction. I'm only allowed to do an algorithm for finding them and for getting this tree. And this tree gives me exactly where are the weakest edges in this graph. Then the precise algorithm is written in the notes. It's very short, but you can try to put the ingredients together and check that it works. All right. So this is an application of this DF search tree. And yeah.
Now our definition, we replace each component by a vertex K, but we need to keep the name of the vertex if we want to recognize the bridges after we create them.
All right, yeah, probably. Indeed, you cannot forget completely the information. But, you know, at the beginning, it depends how you give a label to each vertex or each component or whatever. But you're right. If I want, at the end of the day, if you get this tree, you need to remember with a certain process that this edge corresponds to this one, and this one corresponds to this one. So you're right. You need to be a little bit clever how you label the things. You're right. You should not completely forget the names. Otherwise, you wouldn't know which one is this edge and which one is this edge in the initial graph. You're right. In the implement, but this is part of the code, you're right. Or at the beginning, you probably need to give a name. And so you have to remember that this is between x1 and x2, and this is between x. Yeah, you already see there is a, you have to be careful because I should not use x because this is not a good way because this would have two names. So this is E2 and E5. So you're right, I need to keep track of these numbers. Yes. Okay, so if somebody wants to check this algorithm or how to organize this information, it's most welcome. Let's go to the next section, which is also an interesting algorithm and quite famous. Dijkstra algorithm is quite famous. Spanning tree with minimum edge weights, or yes, edge weight. So I'm going rather quickly, but we have a graph. And now we know what is a weight. On edges, I put a number. Let's say 0.5, 2, 1, pi, whatever, 2, and so on. You can put negative numbers, but we have to be careful, and I will explain why. But a priori, I can put positive and negative numbers. So this is a weighted graph with weights only on edges. We have seen we could also put weights on vertices, but for this application, we have weights, for example, the length of this path. So this is a weighted graph. And now we know that it's undirected. We know we can always construct a spanning tree, and there is not a unique solution. There are plenty of spanning trees. You can wonder, oh, a spanning tree is going to, if I add these weights on the edges of the spanning tree, I'm getting a number. How can I minimize this number? This is the idea of spanning tree with a minimum edge weight. So how can I minimize this total, the sum of the weights on the tree? Okay, this is the idea. And so idea. This is a simple problem at the beginning. Construct a spanning tree. With minimum total weights on edges. And here it doesn't matter if we have negative numbers. And the algorithm here is rather simple. I don't need a complicated one. What do I do if I want to construct such a tree? With fixed. The root is always fixed, with fixed root. Yes, the initial point is always given. what you do when you construct this tree, you can guess in whenever you choose an edge in these frontier edges, in the set of frontier edges, you choose the one with a minimal weight. So the algorithm is, use the algorithm for growing a tree, the one I introduced last week for growing a tree, and choose EI plus 1 in front of GTI with a minimum weight. So whenever you have few edges in this set, all of them have a weight, you choose the one with a minimum, and you continue. And you check that at the end, you get the tree with a minimum total weight. It's not difficult because at each bifurcation in your tree, you took the one with a minimum. So this works. You can check. This gives you the tree with a minimum weight. So this is the easy part. But now we can do something more complicated. If you have any question, you interrupt me. So if somebody wants to prove that it gives you really the only solution, it's not the only solution, because suppose all weights have 1, if all the weights are equal, or if you have 2, yes, if you have 2 in this set with the same weight, you can choose. But still, so it means it's not going to be unique, but the total weight is going to be unique. The minimal total weight is going to be unique. So we have already seen this. The solution is not unique, but the minimal weight is unique.
And your weight of H be negative?
Yes, in this construction, it can be negative, no problem. Yes, as long as it is a fully ordered set. But you will see now in the next step or in the next construction, I have to be more careful. Now the next problem. I fix a subset U inside the set of inside V and construct a tree I'm not saying it's a spanning tree, a tree containing all vertices or all elements of U and with minimal total weight.
I think this must be a breadth-first structure, not a depth.
For this, you can do whatever you want, as there is no relation with the BFS or DFS. Okay, think about it. I'm saying there is no relation in this frontier set. You choose the one with a minimal weight. There is no other things. You don't care if it is minimal x, if the endpoint is xj with minimal or maximal j. It has nothing to do with this. But look, now I'm changing slightly the problem. I'm fixing a few points. And I want to construct a tree which at least contains these points. Of course, it has, in order to get a tree, I need more, but because there is no direct connection between this one and this one, but at least it should contain them. So suppose the solution, I don't know, suppose it is this. Why I have to be careful if I have a negative weight? Because suppose I have a side, okay, let me put -10. Yes, instead of doing this, I can also go before reaching this, which means that each time I go through this cycle has a negative total weight, I decrease the total weight. And of course, I can go an arbitrary number of times, so this has no solution. I mean, the solution would be -infinity. So whenever you have a negative, it doesn't really matter if this number is negative, but you should not have a cycle with a negative weight, with a cycle with a total negative weight. Because if you have a cycle with a negative weight, then you just turn around it as many times as you want, and you lower this total weight. Okay, so just be careful about this. You can have negative numbers, but as long as any cycle has still a positive total weight. Just be careful about this. So let me put a careful no cycle with negative total weight. Otherwise, simply your algorithm will never finish if you do it. So this is another problem. Fix a U, and I'm going to fix the simplest one. I will just fix 2 points. Fix a U and construct a tree containing all elements of U, but with a minimal total weight. I don't know, in this, for general U, I don't know if there is a solution, if there is a clear algorithm how to write it, because it would depend on U, it will depend on the initial graph and so on. So I will simplify my life and take only one initial point x0 and one final point xf. And we will see that this leads to a nice algorithm. So is this clear? Either I put a set U, which is rather big, and I need to find a way to construct a tree containing all these vertices with a minimal total weight. Or now, if I simplify my life, what I'm going to do is to take an initial point and a final point. So U contains only 2 points. And then the tree is going to be very simple in the sense it's going to be a path. So now what I'm looking for is a path from x0 to xf with a minimal total weight. Because I only need to go through 2 specific vertices. So now consider U consisting only of 2 points, x0, and I call it xf for final. And for simplicity, I assume the weight is always bigger or equal to 0. All weights are positive. We can avoid this, but I simplify this. And or maybe I cannot call it xf. Let me keep y. x0 on y. And find the path from x0 to y with minimum total weight. And the path is a very specific tree, so I am still in this section. So I want to go from here, from x0 to y, with a path having the minimal total weight. How can I do it? And how can I do it in a clever way? Which means I'm not going to fix y. I want to do it simultaneously for all y, because we will see that it's meaningful not only to fix this y, so look for this, but also look for the other from x0 to y prime, and from x0 to y second prime. No. Still, it's the same question. From x0 to y with a path of minimal total weight, but y is arbitrary. So I want to because the algorithm is more clever if you do it simultaneously for all y. But still, it's a minimal path between x0 and y, but for arbitrary y. Okay. So let me mention it. Look, the search of this path, this minimum weight path. From x0 to y for all y belonging to G is called the So this guy is Flemish, and apparently his name should be pronounced Dijkstra. Dijkstra. Okay. So it's again about constructing a rather simple algorithm, but in a clever way. So in the algorithm of growing a tree, we denote, because it's going to be an algorithm for growing a tree, we will see. It's going to be a path, but it's the same idea. We denote by O of E, we denote for E inside this front set. The tree endpoint of E by O of E in the non-tree endpoint by T of E. This is completely natural according to the notation I have introduced for oriented graph. Remember, whenever we have a graph on a tree inside, this is, let's say, Ti, I look at edges in the frontier. So we have this one, this one, this one, and this one. These four edges are in the frontier. They all of them have one tree endpoint and one non-tree endpoint. This is a definition of being in the frontier. That's why this one is not in the frontier, because it has two endpoints in the tree. But by definition, in the frontier, you have one endpoint on the tree, one outside. So I'm just going to call, so suppose I call it E. This point is O of E. This one is T of E, even though there is no orientation. If there is an orientation, this would be correct by definition. But because some points are in the tree, some are not, I can call O of E and T of E. The origin of E is the target of E. even though there is no orientation. And now what is this algorithm? So I want to finish, and then I let you think about it. It's KS. Dijkstra algorithm. And there is an illustration in the notes how to implement this. It's quite clever. First, I fix the root, x0 belonging to G. P0 is just one vertex, and the counter is fixed at 0. So this is the same as drawing the tree, the first step. Now choose, and this is the clever part, choose EI plus 1 inside this frontier set. Satisfying okay, I realize I had not introduced one thing, but we will see. I will explain just the notation. I will explain what is the index. Probably I introduced it very quickly. It's a distance, but with a weight. So it's going to be the sum of the weights. It's a weighted distance. So I take, I will explain this. I choose the edge in the front, on the frontier, the minimum between d omega of x0 O of e plus, wait, I finish writing plus omega e. So this is the definition. I haven't introduced.
Distance is between two vertices.
Yeah, but I haven't defined this, but I give the definition. This number, I give this number. But yeah, probably I need to check in my notes what I have written. Probably I have written T like this. Okay, yeah, it's better. But in my notes, I didn't write it. So look at this guy. So what it is, this is the weight of path between the root between x0 and O of E. So we have the root somewhere, x0. So we end up here. Now this is the tree. So as I said, we have all these red guys in the frontier set. By iteration, I have computed the length, the weighted length from x0 to these 2 points here. I have this information. This is the weighted length from x0 to the origins of these red vertices. And now each of them has a certain weight. So let's say this is 1, 2, 3, 4. Oh no, this is pi and 4. We have some weights. So I look at the minimum between this value plus 1 and this value plus 2, or the minimum, I mean, also this from here to here plus pi or plus 4. So I cannot tell you the solution now because I don't know the weighted distance between x0 and these 2 points. But if you do the algorithm iteratively, you have computed this at the previous step. So you have now the weighted distance between x0 and this point, x0 and distance. You can it will either be this one, because this one has an additional length which is smaller than this one. So it will either be this one or this one, because pi is smaller than 4. And you do this iteratively. I will again discuss this next time, and then the point 3 is repeat 2 until this is empty set. But what it means, if you should think about it, when you draw this algorithm, you have to compute several things at each step. I mean, I compute this guy plus this guy plus this guy plus this one, and this one. So I have to compute 4 things. I'm only going to use 1 for choosing the edge, but I should not forget the information, because at the next step, most probably, part of this information will be needed. So you need, and this is explained in the note, there is an example, you need to store the information that you compute at each step in order not to repeat again and again the same computation. But if you do this, then at each, or when you do this until the end, you are going to get as a result the path between x0 and any point in the graph with a minimal weight on the minimal total weight on the path. So it means you have, with this algorithm, if you do it cleverly, you have really the shortest path, but weighted path between the origin and any one. So I encourage you to look at the picture. I will not do the picture on the blackboard because it's too complicated, but there is one page with a picture which explains how you do it and how you implement this idea. I store the information because I don't want to compute it again. And yeah, this Dijkstra algorithm is apparently used quite often because you get a lot of information just by one algorithm. Okay, so I encourage you to look at the notes. If you have any question, you can ask me. Otherwise, we meet again next week. Thank you.
That is the absolute best outcome.
What do you want to prove?
Better than like just doing breadth-first search and then finding.
I'm sure somebody has proved that this is indeed the best algorithm in this. The thing is, you need to store the information, because if you don't do it, you're going to repeat some computation too many times. But if you store this information, it's apparently, yes, best one. Now, if you use a supercomputer or a quantum computer, I'm not sure this is still the best one, but still. Or you prove that it is the best one. Do you have any question online?